Hello everybody, I'm John Doherty. This is one of a series of short videos on the nuts and bolts of using PEST and PEST++. The subject of today's video is the parameter uncertainty file. The parameter uncertainty file is used by a lot of PEST utilities, by PyEmu and by members of the PEST++ suite. Before talking about the details of a parameter uncertainty file, let's just spend a few moments talking about why it exists, what's in it. To do that, we need to talk about Bayes' equation, and I'm sure you're familiar with Bayes' equation. Bayes' equation describes what history matching does. We start off with a prior probability distribution of parameters. We have a likelihood function, which is the contents of which are determined by the amount of noise associated with field measurements. And by history matching, that is, by maximizing the extent to which model outputs agree with field measurements, we obtain the posterior probability distribution of our parameters. So we start off with a prior probability distribution of parameters, we undertake history matching, we end up with a posterior probability distribution of parameters. Now, the prior probability distribution of parameters normally is an outcome of site characterization. Site characterization tells us what we know, what we don't know about the subsurface. We don't know about hydraulic property distribution of the subsurface exactly. It has to be described probabilistically. Thereby, in that probabilistic description, as I said before, we encapsulate what we know, but just as importantly, we put bounds on what we don't know. And the contents, that prior probability distribution of parameters is expressed in a parameter uncertainty file. Now, a parameter uncertainty file can also be used to express the posterior parameter probability distribution. Normally, however, we use it to express the prior. It's worthy of note that that expression of the probability distribution of parameters, prior or posterior, will only ever be approximate. There's a couple of reasons for that. The first is that parameters of a model have to be adjustable. That's by definition, a parameter is an adjustable aspect of a model. These wiggle to express uncertainty. They're adjusted in accordance with trying to achieve the goals of history matching. But because they're adjustable, for example, pilot points or something like that, these descriptors of subsurface hydraulic property heterogeneity are necessarily simplistic, and therefore characterization of their uncertainty is necessarily simplistic. The other reason why the contents of a parameter uncertainty file actually are a simplistic description of hydraulic property variability is because a parameter uncertainty file, as we'll see in a moment, can only contain standard deviations and covariance matrices. These are simplistic geostatistical descriptors. The science of geostatistics is dedicated to deriving much more complicated geostatistical descriptors of what may be under the ground, but these cannot be encapsulated in those simple probability, those simple descriptors like covariance matrices and standard deviations. Hence, as stated here, what we find in a parameter uncertainty file is useful for calibration, history matching, random field generation, but only ever approximate, as is much of decision support groundwater modelling. So let's now briefly examine some of the programs that use a parameter uncertainty file. If you are doing linear, error or uncertainty analysis using members of the PEST suite, there are no shortage of programs which read a parameter uncertainty file. Let's briefly look at PredUnc7. PredUnc7 reads a prior parameter uncertainty file and generates a posterior parameter uncertainty file. To run PredUnc7, you type its name at the screen prompt. It asks for a PEST control file, case2.pst in this case. It asks for a reference variance. This gives it the means to convert weights, observation weights contained in that pest control file, to observation standard deviations, which are used in generation of the posterior parameter uncertainty file. Then it asks for the name of the prior parameter uncertainty file, param.unc in this case. I often call these files param.unc. It next asks for the name of the posterior covariance matrix file that it must generate. We'll talk about covariance matrix files later. And then for the name of the posterior parameter uncertainty file which will cite that parameter covariance matrix file. A question about how it should calculate posterior parameter uncertainties, and then it does the work. Random number generation. There are a number of utilities from the PEST suite which generate random realizations of parameters. The randpar suite is amongst those utilities that generate random numbers. Let's look at randpar2. To run randpar2, you type its name at the screen prompt. It asks for a PEST control file. That's where it finds out the names and something else, other stuff about the parameters that it must generate random realizations of. It asks whether the probability distribution on which basis it generates random realizations of parameters should be uniform or normally distributed. The means of the random parameters. Will they be the parameter values cited as initial values in the PEST control file or midpoints of the parameter bounds? Respect upper and lower bounds when generating parameters? Normally we say yes. Then it asks for the parameter uncertainty file. After it has read that, it asks a few more questions pertaining to what it must do and constraints that must be exercised when generating random realizations of parameters. It asks for the name of the CSV file in which it must store those realizations, the number of realizations required, whether to include initial values in the PEST control file as a realization of parameters in the CSV file, whether that CSV file will encapsulate realizations in rows or columns, then the random number seed, and then it does the work. PEST PPIES. Well, it commences its operations by generating random realizations from the prior parameter probability distribution. It then morphs those random realizations of the prior into random realizations of the posterior. To find out how it generates random realizations of the prior, we give it the name of a parameter uncertainty file. Other members of the PEST++ suite also read a parameter uncertainty file. PyEmu can read and generate parameter uncertainty files. So parameter uncertainty files are everywhere. If we're doing uncertainty analysis, if we're doing random number generation, we don't have to go too far without requiring a parameter uncertainty file. So the next question is, how do we build a parameter uncertainty file? Well, normally just build it using your favorite text editor. As we'll see in a moment, it's not that hard. So what does a parameter uncertainty file look like? Well, before looking at a parameter uncertainty file, let's look at part of a PEST control file. This is the parameter data section of a PEST control file. On the left we have the names of parameters, whether they're log transformed or not log transformed, tied or fixed, initial value, lower and upper bounds, parameter groups, and some other information. Normally there are quite a few different types of parameters in a PEST control file. Some parameters are kind of individual, they're not really related to other parameters. Other parameters definitely fall into groups. For example, pilot point parameters, those pertaining to a particular layer or a particular parameter type, are inherently a group of parameters which should be considered together. Here is a parameter uncertainty file that complements this part of the pest control file. This parameter uncertainty file, its task, as we've talked about already, is to characterize the uncertainty of parameters which appear in the pest control file. A parameter uncertainty file is divided into blocks: standard deviation blocks, covariance matrix block. These blocks can be repeated multiple times. In the standard deviation block, in this case, we are assigning a value of 0.5 times 3 to each one of these parameters drncond1 to drncond3. In these covariance matrix blocks, we are assigning a covariance matrix to these groups of parameters. The covariance matrix in each case is contained within a file that is cited in the block. Construction of covariance matrices is the subject of another video. Now, an important rule is that if any parameter is adjustable in the pest control file, that is, if its partrans value is log or none, then it must be cited in the parameter uncertainty file. It must have a standard deviation or covariance associated with it. If it's fixed or tied, it doesn't have to have an uncertainty associated with it. Meanwhile, a parameter uncertainty file can include other parameters that are not cited in the pest control file. They are simply ignored by programs which read a parameter uncertainty file. Let's look at some other important protocols. The first one is that if a parameter is log transformed in a pest control file, for example in this pest control file they're all log transformed, then uncertainties that are provided in the parameter uncertainty file must pertain to the logs of those parameters. So this standard deviation of 0.5 must pertain to the log of each one of these parameters. Variances and covariances in the covariance matrix file must pertain to the logs of these parameters groups. The log to base 10. Conversely, if the partrans value is none, then these standard deviations and variances, covariances pertain to the native parameters. The second important factor is that these covariance matrices, the covariance matrices that are provided in these covariance matrix files, must be positive definite. Now, not just any old matrix will do. Ensuring positive definiteness can be difficult, but it happens automatically if the covariance matrices that are contained in these files are generated using utilities, for example, from the ppcov suite supplied with the PEST groundwater utilities, by plproc or by pyemu. So this is normally not a problem for us because we use these programs to fill these files. Something that may be useful is that optionally included within each one of these blocks may be a multiplier keyword followed by the value of a multiplier. So for example, in this standard deviation block, the multiplier is 3. Any program which reads this parameter uncertainty file will multiply all these standard deviations by 3 in providing prior uncertainties to the program which reads it. In this case, all elements of this covariance matrix are multiplied by 2 when supplying variances and covariances to the program which reads this file. Just beware when supplying multipliers that variance is the square of standard deviation. Hence, if you multiply variances by 2, you are in fact multiplying standard deviations by the square root of 2. Finally, just to repeat something I said before, a parameter uncertainty file can have many standard deviation blocks and many covariance matrix blocks. Let's focus on covariance matrix blocks for a few moments. So the question is, how do we link the elements of a covariance matrix to the parameters in a PEST control file? There's 3 ways to do that, and these 3 ways are exemplified in these 3 covariance matrix blocks. So, the first way. To demonstrate this, let's look at a covariance matrix file. Now, this is the subject of another video, and remember that covariance matrix files are large. They have a lot of elements. If a covariance matrix file pertains to, for example, 104 parameters, then it will have 104 times 104 elements. So these are large. We're only showing we're showing a lot of it, the covariance matrix file with a lot of it left out here. At the start of the covariance matrix file, we have a row comprised of 3 integers. Number of rows, number of columns, and a little code here which tells us something about the covariance matrix to follow. Now, PEST matrix file protocol allows you to have, following the actual matrix, a little header called row and column names. And following that header can be the names of the parameters to which the rows and columns of the covariance matrix pertain. If this covariance matrix is built by the PPCOV family of utilities supplied with the PEST Groundwater Utility Suite, this suite of utilities provides you with the option of linking pilot point names, because these utilities read a pilot points file, of linking pilot point names to the parameter names by adding a little prefix to the name of the pilot point name to obtain the name of the parameter. So the linkage between rows and columns of this covariance matrix file and parameter names is built into the file itself. These names are in the same order as the rows and columns of the matrix which precedes it. They do not have to be in the same order as in the PEST control file. Hence, a program which reads this file is prepared to reorder that matrix if it needs to. Let's look at the second option. In this case, we provide a list file together with the covariance matrix file. So here's our covariance matrix file again. This could be built by the PPCOV suite. It could also be built by PLProc. It could also be built by you using a program that you have written. If this protocol for linkage of row and columns to parameters is adopted, this part of the file is ignored on reading the matrix file. If it's present, it's simply not read, or it doesn't have to be there at all. In that case, you have to provide a list file with the names of the parameters. The ordering here has to be the same as in the covariance matrix file. It does not have to be the same as in the PEST control file. So once again, the program which reads the covariance matrix file is prepared to reorder the rows and columns of the covariance matrix file if it needs to, if this order differs from the order of parameters in the PEST control file. The third option is exemplified in this third covariance matrix block. This is actually the option that I use mostly. Here, within the block, are two keywords, first parameter, last parameter, followed by the name of a parameter from the PEST control file. So going back to our covariance matrix file, if row and column names follow the actual covariance matrix, this is ignored. So this file could be written by any of these programs or by yourself. Instead, the linkage is made on the basis that this is the parameter pertaining to the first row of the covariance matrix, this pertains to the last row and column, and the order of parameters in the PEST control file is the same as the order of rows and columns in the covariance matrix file. And of course the number of parameters and the number of rows and columns must be in accordance. Now, this isn't too hard to do actually. Normally programs that build a covariance matrix file read a pilot points file. Building a PEST control file, you read a pilot points file. So ordering will normally be maintained, and normally pilot point names are indexed and will be in increasing value, so it's easy to check that ordering has been maintained. So this is normally, I find, the simplest way to provide that linkage between contents of a covariance matrix file and parameters in a PEST control file. Finally, how do we obtain these parameter statistics? Well, this is really up to your expert knowledge, but there's some things which may help. Let's look at standard deviations first. Suppose that you're the type of person who wants to set the lower and upper bounds of parameters to be realistic. That is, you don't want these parameters to adopt stupid values as they're estimated by PEST or adjusted by PEST++. Now sometimes I set these bounds very wide because if PEST insists on giving them stupid values, that tells me something. Or you may prefer to set them realistically in accordance with the innate variability of these hydraulic properties. Well, if you do that, you're actually saying something about the prior probability distribution of these parameters. For example, the lower and upper bounds may define the 95% confidence interval of this parameter, in which case, on the assumption of a Gaussian probability distribution, divide the difference between the upper and lower bounds by 4, that's 4 standard deviations, to obtain the standard deviation that you'd use here. And then get rid of that standard deviation multiplier. That should only be 1 if you're dividing the difference between these by 4. So in this case, these are 2 orders of magnitude apart, and this is 0.5. Don't forget that the standard deviation must pertain to the log of this parameter because it's log transformed. So we take the log to base 10 of the upper bound, log to base 10 of the lower bound, divide that difference by 4. This is 2 orders of magnitude, standard deviation 0.5. The multiplier should be 1 or leave this out. For the covariance matrices, well, that's a little different, and we talk about covariance matrices in another video and how you assign the variance of parameters, spatially distributed parameters. But just a note of caution here, the variances contained in these covariance matrices describe the innate variability of these parameters. And that variability should be kind of commensurate with the bounds. That is, we don't want parameters to be described, for example, as quite variable in these covariance matrices, but for their variability to be then limited by these bounds. Make sure these bounds are wide enough to accommodate the variability expressed by the covariance matrix. And in doing that, in making that comparison, don't forget, covariance matrices express variance along their diagonal elements, which is the square of standard deviation. So you have to take the square root of variance to obtain standard deviation to make a comparison with upper and lower bounds as expressed in the PEST control file. And that brings us to the end of this video on parameter uncertainty files.